Hi, and good day. Now, we continue our lesson to the physical properties of carboxylic acid. These are the learning outcomes of the lesson right now. The first physical property that we discover is the boiling point of carboxylic acids. If there are a series of organic compounds that with comparable or almost similar molecular size, the boiling point of carboxylic acid will be higher than that of alcohol, aldehyde, and ketone. Both alcohol and carboxylic acid have intermolecular hydrogen bonds, but the carboxylic acid forms stable hydrogen-bonded dimers. Carboxylic acid molecules and dimers are arranged closely packed. Therefore the hydrogen bonds are relatively strong. Hence, higher energy is needed to overcome more and stronger hydrogen bonds and dimers results to the highest boiling point of carboxylic acid. Second, the solubility of carboxylic acids. Carboxylic acids are soluble in water due to the formation of intermolecular hydrogen bonds between the water molecules and the carboxyl group of carboxylic acid molecules, called hydrophilic area. The solubility of carboxylic acid in water is almost the same as alcohol due to the presence of hydrophilic area. However, the solubility of carboxylic acid in water decreases due to the increasing size of alkyl group, called hydrophobic area in the carboxylic acid. Benzoic acids are slightly soluble in water due to the presence of benzene ring, a huge hydrophobic area which reduces the solubility of benzoic acids in water. Dicarboxylic acids are relatively more soluble than carboxylic acid since more hydrogen bonds are formed in between dicarboxylic acid and water molecules. Carboxylic acids are soluble in nonpolar solvents such as benzene due to the formation of intermolecular van der Waals forces between the benzene molecules and alkyl group of carboxylic acids. Carboxylic acids are soluble in polar solvents such as ether and alcohol through to the formation of intermolecular van der Waals forces between the ether and alkyl group of carboxylic acids, or intermolecular hydrogen bonds between hydroxyl group of alcohol and the carboxyl group of carboxylic acids. Third, the acidity of carboxylic acids. The acidity of carboxylic acid is influenced by resonance effect and inductive effect. Carboxylic acid molecules dissociate in water to form carboxylate ion and hydronium ion. The negative charge in carboxylate ion are delocalized effectively between two electronegative oxygen atoms, which stabilizes the carboxylate ion and promotes the release of hydrogen ion from carboxyl group. Due to the resonance stabilization of the carboxylate ion, carboxylic acid is more acidic than phenol in alcohol. Phenol molecule dissociates in water to form phenoxide ion and hydronium ion. The negative charge in phenoxide ion is delocalized less effectively in between more electronegative oxygen atom and less electronegative carbon atoms in the benzene ring. The resonance structures of carboxylate ion is more stable than that of the phenoxide ion. Therefore, carboxylic acids are more acidic than phenol. Alcohol dissociate in water to form alkoxide ion. Alcohol is the least acidic compared to carboxylic acid and phenol due to no possibility of delocalization of negative charge, and the electrons are localized at oxygen atom in alkoxide ion. Hence, alkoxide ion is not stable compared to carboxylate and phenoxide ions, and hydrogen ion is not likely to be released. Therefore, the most acidic compound is carboxylic acid, followed by benzoic acid and water, then the least acidic is alcohol. The substituent groups that attach to the carbon atom in the carboxylic acid play an important role in determining the acidity of the carboxylic acid. The substituent groups can be classified as electron withdrawing group and electron donating group. An electron withdrawing group that attached to a carbon atom will stabilize the carboxylate ion and increase the acidity of its carboxylic acid, while an electron donating group that attached to a carboxylate ion will destabilize the carboxylate ion and decrease the acidity of its carboxylic acid. Electron withdrawing groups reduce the electron density of OH bond in the carboxyl group of carboxylic acids. Thus, the OH bond in the carboxyl group becomes weaker and hydrogen ion can be easily released and form a stable carboxylate ion. The carboxylic acid is said to be more acidic than that without electron withdrawing groups. 2,2-dichloropropanoic acid contains 2 chlorine atoms, more electron withdrawing group, which creates a greater inductive effect and makes the OH bond in the carboxyl group weaker than that in 2-chloropropanoic acid. Thus, the hydrogen ion in 2,2-dichloropropanoic acid is easier to be released. As a result, 2,2-dichloropropanoic acid is more acidic than 2-chloropropanoic acid. The distance between chlorine atom and carboxyl group in 2-chlorobutanoic acid is nearer compared to that in 4-chlorobutanoic acid, which will gives a greater inductive effect of withdrawing electron density from the carboxyl group. The OH bond in the carboxyl group of 2-chlorobutanoic acid becomes weaker than that of 4-chlorobutanoic acid. So, the hydrogen ion in 2-chlorobutanoic acid is easier to be released. As a result, 2-chlorobutanoic acid is more acidic than 4-chlorobutanoic acid. Alkyl group is an electron-donating group. The ethyl group in propanoic acid is larger than that of methyl group in ethanoic acid. So, ethyl group is a stronger electron-donating group than methyl group. The electron density of OH bond in the carboxyl group of propanoic acid increases and the OH bond is strengthened. Thus, the hydrogen ion in propanoic acid is more difficult to be released. As a result, propanoic acid is more acidic than ethanoic acid. This is the summary of how inductive effect of substituent groups influence the acidity of carboxylic acids. These are the enhancement exercise. Students are required to do it and refer to your tutors to check the answers. That's all for this session. Thank you, and good day.